Hello everyone. Our today's topic is different forms of Nernst equation. In our previous topic we have studied how to prove the Nernst equation. So here I have written there the conditions. It is used to calculate the electrode potential of a cell when the concentration of ion and the standard electrode potential is given. So let us consider the equation Mn positive plus n electron gives M in a solid form. That means this represents the metal ion in aqueous form and this represents in the solid form. So if it will accept n number of electron, so that will convert into a M. So the Nernst equation which we have proved yesterday, so that E is equals to E naught cell minus 0.0591 upon n log 1 upon metal ion. So here it is to be written here the molar concentration of product divided by the molar concentration of reactant. If we will see this equation, the molar concentration of product, that is to be represented by M, and it is to be a reactant, so it is to be written here Mn positive. So here it should be written here M upon Mn positive, but I have taken here the molar concentration is unity, so 1 can be written. So this is the one form of the Nernst equation which is to be used to calculate the electrode potential for a single metal electrode. Okay, where n represents the number of electron, Mn positive represents the molar concentration of ions. Let's come on the another form of Nernst equation for a cell reaction. We know that every cell reaction completes into two portions, oxidation and reduction. Always on anode oxidation takes place and on cathode reduction takes place. So it is used to calculate the EM of a cell when standard electrode potential of electrodes and concentration of ions at cathode and anode are given. So let us consider the one cell equation. Zinc is going to be oxidized Zn2 positive. This represents the salt bridge, and Cu2 positive, that is going to be reduced to copper. So we will use there the Nernst equation. E cell is equals to E naught cell minus 0.0591 upon n log anode over cathode. So on anode always oxidation takes place and on cathode reduction takes place. So the oxidation of Zn ion is taking place and the reduction of Cu2 positive ion is taking place. So we will put in place of anode and cathode Zn2 positive and copper 2 positive. So this is the another form which we can use to represent the Nernst equation. So now the third case, Nernst equation and the equilibrium constant. So let the cell reaction consider Zn plus Cu2 positive gives Zn2 positive plus Cu. So the equilibrium constant, this is the ratio of the molar concentration of product divided by the molar concentration of reactant. So I have written Zn2 positive upon Cu2 positive because Zn2 positive is product here and Cu2 positive is reactant here, and molar concentration of ions are to be considered because I have mentioned in aqueous condition. So at equilibrium, the E cell will be 0. So now, as we put in the Nernst equation, E cell is equals to E naught cell minus 0.0591 upon n log Zn2 positive upon copper 2 positive. Okay. So now, in the second case, now E cell we will put there the value 0 and E naught cell, then rest of the reaction remains same. So this reaction can be written in this form: E naught cell equal to 0.0591 upon n log Kc. If it should be multiplied by this term, so we will get the log Kc is equals to E naught cell. It should be multiplied with E naught cell n and divided by 0.0591. So this is the another form which shows the relation between equilibrium constant and E naught cell. So depending upon the number of ions exchanging or the number of electrons exchanging, the value of n should be kept here. Now we are coming on the next condition. At equilibrium, E naught cell value will be 1.10. This already I have taught in the class. Three conditions were there. The value will be greater than 1.10 and the value will be equal to 1.10, and the third case value will be lesser than 1.10. But here we are considering the condition of equilibrium where the value of E naught cell will be 1.10 volt. So if we are putting this value in this equation, so in place E naught cell we will put there 1.10 into n upon 0.0591. So in this equation, two ions are producing. It means the value of N will be 2. So we will put there the value of N is equals to 2. So here log Kc is equals to 1.10 into 2 upon 0.0591. If we will solve this whole term, we will get a number 37.288. So when the log is converted into antilog, so that can be written, log will move here, that convert into antilog. We have to find out the value of Kc. So that can be written in this form, antilog 37.288. So now how this value has come, now I am going to tell you once again. That the number, as I taught in the class, the number which comes before the decimal in antilog, that goes into 10 raised to the power. So the number 37 is written, that goes into 10 raised to the power 37. And you open the antilog table and you see the value 0.28 on 8. You will get the number 1936, and decimal always is to be put after one place. So we are getting a number 1.936 into 10 raised to the power 37. Or in the approximation, this value we can write Kc is equals to 2 into 10 raised to the power 37. Okay. So the homework for today, the first question, how much electricity in terms of Faraday is required to produce? How much electricity in terms of Faraday is required to produce? So the question is given 20 gram of calcium from molten calcium chloride. So whenever this calcium chloride is to be ionized, that will ionize Ca2 positive plus 2Cl negative. So here if you will see there, the number of electrons will be 2. And the actual mass of the calcium is 40. So 40 gram of calcium will produce charge 2F, because the value of formula of charge is NF and the value of N will be 2 here, and no need to put the value of Faraday because they are asking the answer in terms of Faraday, not in the Coulomb. But in the question they are asking the 20 gram of calcium. So we will apply there the unitary method, that 40 gram of calcium will produce 2F charge, then 20 gram of calcium will produce 2F into 20 upon 40. When we will solve it, then we are getting the answer 1 Faraday. In the same manner, that the next question is to be solved. This is 40 gram of aluminium from molten Al2O3. So first of all, you have to ionize this equation, find out the value of N and put in the formula and try to get the answer.